Okay, as it says, post-hoc testing and contrast testing. So what to do after your ANOVAs. So we'll start off by looking at what does a one-way ANOVA test and really trying to work out how we can tell what's going on. We're going to have to adjust for multiple comparisons. So we can do this in one of two ways. We can change the alpha level, so the point at which we'll call something significant, or we can use what's called the Studentized Range. Okay, so there'll be the basic frameworks for how we can look after getting a significant effect in an ANOVA as to what's going on, what means are different from what means. We'll then look specifically at post-hoc testings, so at the adjusting the alpha level, there's Bonferroni, Sidak, Sheffer. We'll look at studentized range methods. The standard one that's recommended is Tukey's HSD, honestly significant difference. Whether it truly is honestly, it doesn't matter. Neuman Keuls is another one. Then we'll move on to look at what you do with two-way ANOVAs, specifically what one does with the interaction terms in an ANOVA. That's what you do if you haven't set up a priori a set of predictions. Whereas we can also do some specific hypothesis testing following an ANOVA. And this is obviously the preferred approach because simply we are aiming to answer a specific test, a specific hypothesis. And they're contrasts or planned comparisons from the textbook. So a quick reminder of a one-way ANOVA. What we're trying to do is work out what causes the variability, the variance, in the dependent measure. And we're going to assume that some of that is due to the different levels of the factor. So the effect of the means differing from each other. If you remember, the F ratio is looking at two estimates of the standard deviations, the variance of the means. The direct method goes on top, so it's the difference between the mean of a level and the grand mean, x minus x bar squared. And we're going to divide that by the variance that you would estimate of that from assuming the pooled variance, the independent and identically distributed one, and that's our noise variation, the variation that we expect to see from the noise, the random error, the stuff that we assume to be outside of the experimental control. So just the inherent noise in our variable. Remember, in ANOVA, we've made the assumption of this multitude of different little processes, and we're targeting one of them. We're trying to manipulate something and to see if we can cause a detectable change in our dependent variable by changing one of these processes, so one of three levels in this example. And if the experimental manipulation has influenced a process, what we should see is that the mean of otherwise identical distributions will differ from each other. So just by biasing one of those processes, we can shift the dependent variable either up or down. We can think of this in a one-way ANOVA as having a grand mean, so our overall central point, and then each level of the factor will shift the mean to its appropriate level. So we have level A mean shifting the dependent variable down, level B shifting it up, and a little error term. So we're going to model this as the observed value is the grand mean plus level effect plus an error term. And if you remember, you can actually fill in a grid for every data point. Where we have this, notice that although there's levels A, B, and C here, we're assuming that all of the error terms come from the same distribution. So in this example, we can label them the error term epsilon 1 to 16. When we run the ANOVA, we get our variance table, and with it we can see if the p-value of the f equals 1, remember because we're estimating two estimates of the same thing, the standard error of the mean as a variance, standard mean square between divided by the mean square error. Those are both estimates of the same thing, it should be 1. If the probability of getting that value by chance is smaller than our alpha level, 0.05, what we can conclude is that in some way the means are not equal. in some way there's a difference between the sum of those means, but we don't know in which one is different from the others. Okay, so we're going to look at two different classes, two different ways of looking and examining the differences. Post-hoc tests are ones which are post-hoc after the event. Okay, and we should only look at post-hoc tests if the ANOVA is significant. Okay, the ANOVA tells us something is going on, and then we can look to see what it is. We can use the post-hoc test to explore what the ANOVA is telling us. Contrasts or planned comparisons are more powerful. They're a better, if you like, way of doing things. We're more likely to be able to detect the differences that we want. They can be done in the absence of the ANOVA being significant. We've set them up beforehand. It is generally not such a good idea to do so. We want the ANOVA to say there is a difference and then look for what the specific differences are. The beauty of planned comparisons of contrasts is that you can use them to evaluate very specific predictions. Okay, so some of you in the afternoon sessions should be setting up these and thinking exactly how you are going to examine the dependent variable that you're actually interested in, rather than just a dependent variable that you're measuring directly. You have various effects that you will want to work out what the effect is and ask if that effect is a significant effect. Multiple comparisons. So, if we look at the chances of, think of the chances of getting an error, that is saying something is significant when it's not. If you're doing all pairwise comparisons, if you have two levels in a factor, well then you've set the alpha level at 0.05, you're only doing one comparison. And so the chance of making type 1 error is 0.05, it's your alpha level. If you have three levels in a factor, you can compare A with B, A with C, and C with B. You can do three comparisons. And that raises the chance of one of them coming out as being significant to about 0.15, or thereabouts. If you have four, it goes up to just over 0.2 and so on. Now those are very different from the alpha levels of 0.05. As you can see, if you've got 5 or 6, you've got a 50% chance or thereabouts of detecting a difference between a pair of means that is not really there. So we need to do something about that problem. We need to control for the problem of doing multiple comparisons. One class of doing this is to adjust our alpha level. The Bonferroni correction, which is the one that's standardly used, I'm not quite sure why, is that you look at the number of pairwise comparisons you're going to do and divide the alpha level by it. The reason why we use that is that not that long ago, it was much, much easier to do that calculation, remember all of these had to be done by hand, than doing the correct calculation, the correct correction rather, which is Sidak's correction down at the bottom. They work out as having very, very little difference between them. But one of them is correct and the other is a very good approximation. So although Bonferroni is the standard one, I personally don't see the point in using it because I can click the box that says Sidak's correction just as easily, and I know exactly that that's controlling for pairwise these multiple comparisons exactly. Scheffer's correction is more extreme, if you like, more severe, because it looks at all possible linear combinations. You'll see in some of the background slides the examples of the linear combinations. There are a huge number of them, particularly when you've got 4 or 5 or more levels of a factor. Okay, so it is conservative unless you are going to do every one of those comparisons. Scheffer's becomes Sidak's, but Sidak you just say, I'm going to do all of the pairwise comparisons rather than all possible linear combinations. Okay, when you're running ANOVAs, if you look in the post-hoc option, if you've got between subjects factors, you can click on the relevant post-hoc tests. You can also run and do the compare the means in one of the boxes, which will allow you to apply some of or any of these corrections to the terms that you're going to do, to correct for the fact you're doing multiple comparisons. We tend not, in psychology, to do this. Okay, it's perfectly legitimate, but we do tend to adopt the techniques that use the studentized range. Okay, what's this studentized range? If you draw two samples from the normal distributions, you can look at the difference between the means. Okay? And then you can repeat that over and over and over until you have the distribution of the differences. Okay? This is actually just what a t-test is doing. That's a t-distribution. If you have 3 levels, you can draw 3 samples and take the difference between the largest and the smallest and get the distribution of that. If you have 4 levels, you can take 4 samples, take the difference of the means between the largest and the smallest and generate that distribution. Okay, so it's like doing a t-test, but you're saying, well, actually, we've drawn 3 samples or 4 samples, we've drawn however many samples that you have. Okay, the distribution will have larger values and be wider the more samples that you get, simply because the chances of getting a particularly big one and a particularly small one increase just as you're getting more and more samples. Okay, so this is actually appropriate when you are comparing the means having drawn 3 or 4 or 5 samples. Yep, different levels of your factors. Okay, the critical value, that's the value that you need to exceed for your statistic to be significant at the 0.05 level. Okay, well, decreases as the sample increases and increases as the numbers of levels increases. Okay, and if you just think of it with 2 means you've got 1 pairwise, with 3 means you've got 6 pairwise, with 4 means there's 10 pairwise comparisons. Okay, no, it's actually doing this comparison set for you. So rather than thinking of it in terms of the numbers of comparisons, the studentized range is taking that into account and saying what's the biggest difference that you need. Okay, here's some simulations just to give you an idea that even if you run this with 100,000 samples, you've still got a very wobbly distribution. That distribution is theoretically nice and smooth. Unfortunately, it doesn't have an analytic solution, and programs like SPSS and so on use very complex and very accurate algorithms to work it out. But essentially, they're doing this thing of drawing, say, 4 means millions and millions of times and generating that distribution. So you can see with the difference here as you go from 2 means to 3 means to 4 means. You can see the differences. Again, we're going to always express distances standardized. We're going to divide by the standard error of the means of the IID. Look at those distances. You can see that as you get moved from 2 to 3 to 4, you're likely to get bigger differences between the means, but it does follow a systematic shape. To convert those distributions into the probability values, as always, we actually put them into a cumulative form. And then for any standardized distance that we have between the means, you can read off the likelihood of getting that distance or greater. You can actually read off the difference of getting it smaller than that distance. Okay, so we're just treating this, it is just another statistic, but it's drawn and developed in a slightly strange way that doesn't have an analytic form, it doesn't fall neatly into the Neuman Keuls style of statistics. There's no neat analytic solution. Okay, so we've got these 2 things just to say it's always better to only do post-hoc tests. You have to do them only if the ANOVA is significant. Don't do them if the ANOVA is non-significant. Okay? The ANOVA tells you something somewhere is different if it's significant. So post-hoc tests that are based on the assumption that there's no effect, and that's what we've just been looking at, are going to be actually slightly conservative. So if you're making sure that the ANOVA is significant and then do your post-hoc tests, try to find out where that difference is, we know that they're going to be slightly conservative because all of these have been based on the assumption there is no difference. The studentized range, you're drawing 3, 4, 5, 6, however many samples that are themselves all identical and looking at the differences. Okay, so we can adjust either by changing our alpha level or the studentized range. I would love to be able to say which one to do and always how to do it. It does vary. When we adjust the alpha level, we actually use the t statistic, we do a t-test, to compare things. All we're going to do is change the alpha level. Okay, so we're going to look at the difference, and the t-test, we're looking at the difference between two means, standardized by dividing it by the standard deviation of the difference between the means, so the standard error of that difference. And we calculate that standard error of the difference using the usual things of 2 times the mean square error. So we're actually doing mean square error 1 plus mean square error 2. Comparing two variances always add. And we divide it by the harmonic mean of the ends in the different samples. So we just do a t-test. We evaluate the probability of the t value of the difference equaling 0. And it has the error degrees of freedom. I recommend using Sidak's correction. Remember, it works under the assumption of there being no difference between the means. So it is slightly conservative, which is always what we want to have. And it makes sense in that we're doing the correct correction for the number of comparisons. If we do just alpha, we use the t-test. If we're using this studentized range, Tukey's HSD, honestly significant difference, is the preferred option. We calculate essentially the studentized t statistic, which is often called Q. You might see it as TS, meaning it's using this standardized ones for the numbers of samples that you've drawn. You'll see that its formula looks remarkably similar to a t, the t value, which it is indeed, but now you have a pair of degrees of freedom. One is the numbers of samples that you have drawn, and the other is the degrees of freedom from the error term. So the Q statistic depends on the numbers of means that you're looking at, the numbers of levels. And in the same way, we're going to evaluate, the computer evaluates for us, the probability of the Q statistic being 0, but it uses this standardized range distribution. And it, not surprisingly, that in fact Q and T are related when there's only 2 levels. Neuman Keuls is another one that you might come across, particularly in some of the older articles. Neuman Keuls is still using the standardized T1, but it does something rather sort of strange. Again, there's lots of little background slides to show you how. You first order the means of the levels. Okay, so you've got x1 is less than x2, which is less than x3, and so on, all the way up to your xn. And then you look and use the number of means that there are between. So you start off and you compare x1 with xn, and you ask, x1 with x2, x2 with x3, and so on. And you have n equals 2. You can then look at x1 versus x3 with n equals 3. So in fact, you start at the big end, and you say which ones, how many of these are different, and narrow it down. So each time you do a comparison, You're looking at the number of means in your distribution that you've got. So if you compare x1 with xn, you've drawn a sample of n means. If you can compare x2 with xn, or x1 with xn minus 1, you have n minus 1 samples that you've taken to look at. So it's a slightly more powerful method than Tukey's HSD. By powerful, I mean you're more likely to detect differences if they're there, because Tukey's HSD says looking at x1 versus x2 is the same as looking between x1 and xn. This one says no, they're not. In one, you know you've only got 2 drawn together, 2 samples versus the n. But it means that you lose some control over type 2 errors. That is, saying things are different when they are not. So we can start off with 6 values. We can compare x1 with x6 and go, oh, that's a difference that's significant. And then we can compare x1 with x5 and x2 with x6. x1 versus x5 is significant, so we compare x1 with x4. If that's non-significant, we know that anything involving x4 and the numbers less than it won't be significantly different. What we predetermine. So we cut out that set of comparisons, and then we can do all of the comparisons along. When you're doing these things, you'll see figures that look a bit like this, where people have gone, x1 and x4 is the same, so we'll link those. x2 and x4 come out as being the same. x3 versus x5 and so on. You try and draw a pattern out to make sense of it. Tukey's HSD in SPSS will put out a table that's sort of twisted round a bit, but it groups them together for you. So you can try and then describe the pattern of which means are different from which other means. Okay, so post-hoc tests. We're going to have to, in one way or another, adjust for multiple comparisons. If you're going to adjust the alpha level, use Sidak's method. Tukey's HSD is the favoured one for the studentized range. And it always uses the number of levels in the factor. It's because we know how it controls for the type 1 and type 2 errors it's set. Neuman Keuls, say you might come across in, particularly in older papers, it has more power, it's more able to detect differences that are there. It is less conservative than Tukey's HSD. Okay. And it varies the number of means according to the number of means within the range under consideration at any one time. So that means you've got unknown type 1 errors, unknown errors of there's a difference, you claim there's a difference when there isn't really a difference. Okay, so just in this you can see that we can pull out 3 and each of them has different properties. So, for instance, just saying, should we use Tukey's HSD or Neuman Keuls, would you have to make a judgment call as to what's the worst mistake? If it really matters, so if you're dealing with something where what really matters is detecting effects, and it's not the end of the world if you say there's an effect, but there isn't, you make a type 1 error, well, go with Neuman Keuls. It's more likely to let you see differences that are there. You're less likely to miss something. But of course, in some instances, the reverse is true. You actually need to be really sure of an effect. So if you think of something like drug trials, if you are testing a drug to replace something that you know sort of works, you want to be absolutely certain that the one you're replacing it with, your new drug, works better. Because a new drug, you won't know all of the side effects and so on. These are well known for the old drug. So there you want to play a conservative game. You want to say, look, I'll recommend this new drug only if we're sure it's better than the old drug. If there is no old drug, now the game's changed. You're going to go, well, what we want to do is have something that works, or that might work. because it's better than not giving a drug at all. We can give a treatment, we're not absolutely certain it's going to work, but we're pretty sure it's better than no treatment. Okay, so in that case, you want to use a different set of criteria. The balance between type 1 and type 2 errors changes from study to study. So there is, unfortunately, no simple answer on how to do it. There is one situation where using Neuman Keuls or Tukey's HSD really does not make sense. Okay? And that's when your independent variable is related to particular values on what you can think of as being a continuous scale. If you're dealing with dosages, durations of stimulus exposure, degrees of rotation of an image, changes in stimulus contrast, these are all things that are on a continuum. Okay, so if we take something like rotation, we can have two values, 0, which is upright, and 180 degrees in inverted image. Or we could have 8 values, 0, upright, and then going around in 8 steps until you get to inverted, upside down. Okay, so I've got different numbers of levels, but they're bounded in this case by the same values, 0 and 180. You can't go more than upside down. Okay, so it's not appropriate because with 2 levels, if you do a Tukey's HSD, you make it just a t-test. With 8 levels, you require the difference between 0 and 180 to be bigger than if there were 2 levels. And there's no reason to expect them to be bigger. Just because you've tested halfway between, or 1/8 of the way between, shouldn't increase the means to 0 and 180. If you're dealing with doses of drugs, if you give a 0 level, a placebo level, and the maximum level that you regard as safe, I don't know, say 10 milligrams per kilogram of body weight, something like that, if that's the maximum safe level, you might want to find out what happens at halfway between. Giving a different group of patients a halfway between dose shouldn't make the patients that had 0 be less, or the patients that get 10 milligrams per kilogram of the drug more. So it makes no sense to adjust your testing. So that, again, just this idea of what test do you use? Well, you have to think about the relative value of type 1 versus type 2 errors. And you have to think, do we need to just shift these around, or should we use the studentized range? Does it make sense that every level we've tested should just be different, that they're not on a continuum? If they are on a continuum, the studentized range doesn't make sense to use. The 0 and the maximum dosage that you can give safely is fixed. If you give values in between, it's not and shouldn't be regarded as changing those means. Okay, now there are even fancier ways of dealing with them. For the moment, just think of it in terms of dealing with the change. You either change the alpha level or you use the Neuman Keuls or Tukey's HSD. Okay, so here's an example to reiterate this point. We've got 2 levels of rotation, 0, upright, 180 degrees, inverted, or 10 levels that we could have of them. We can use the adjustments to compare 0 and 180. They're the same conditions, they should have the same means, the distances should be the same. And in the 2-level case, the critical value is T is 2.09. It's with 20 participants, 20 estimates per level. With the 10-level case, if we use Sidak's correction, slightly less extreme, slightly less conservative than the Bonferroni one, that T value goes up to 3.8. So that's saying that if we make this correction, just because we've tested intermediate values, we now need to have a difference which is 1.8 more standard deviations. It doesn't make sense to do that, because the means in the 0 and 180 should be the same. So people's obsession with making corrections for multiple comparisons uniformly comes from not understanding what the comparisons are making and how the changes that they're making affect the result. There are situations like this where it makes no sense to increase the difficulty of getting something. You should to some small extent, but we don't know by how much. One should always use a less conservative estimate in these situations where you've got a continuous independent variable and you're testing at multiple levels along that, but the ends, the extremes are still bound. They shouldn't be changing. So I'm actually a fan of the one that every textbook will say you really shouldn't use, because in most studies you shouldn't use it. But the unadjusted one, the protected least significant difference, is the one where you go, I'm not concerned if I say there's a difference and there it turns out not to be ultimately, and I'm doing a test along some sort of a continuum. So there's always intermediate values I could add in which shouldn't change the likelihood of what comes out as being different too much. Okay, it's protected because you really make sure the ANOVA is significant. Say, I'm only going to look after a significant effect is reported by the ANOVA. And it really is analogous to a t-test, it's just not making any corrections to an alpha level. The other reason that I like it is that it's based on the assumption that the ANOVA uses of independent and identically distributed error terms. So when we do these tests and then change the way that we test, we go to the studentized range. The way that SPSS does these comparisons doesn't even use the pooled variance estimates. It'll do actual t-tests using the distributions for each of the variables. It won't pool the estimates. Yet it has done the ANOVA, which has pooled all of the estimates. So it sort of goes, I'm going to do a test and it's fine for one bit, but then I'm going to pretend it's not fine for another bit. Okay, so it's one way, if you have this idea of a continuum, of getting round it, so long as it doesn't matter if you say it looks as though there's a difference and there isn't really. So you can't make particularly strong claims about a particular difference. You need to look, as always, at the pattern of differences and use the protected least significant difference. Okay, so we just calculate a t-statistic using the error terms that are there. This is going to be an important thing when we come to look at main effects, when we come to look at interaction terms in more complex ANOVA designs. And we're going to use this idea of we're comparing two means, which we can estimate as the mean square error divided by n, or square rooted. Okay, so we can use this idea. We've got two of them. Variance is add for independent. That's why it's important that they're independent error terms. For independent error terms add. So the variance between two means is going to be twice the variance associated with each error term, with each mean rather. So 2 times the mean square error divided by the harmonic n. It's like dividing just by the n. If you remember a few lectures ago, I took you through why we use the harmonic mean of the n's to allow for different sample sizes in each one. And we calculate the t value. We're using all of the degrees of freedom of the error term. We've pooled, so we've got more degrees of freedom than if we just use the individual samples. And we just look this up on a t-table. Of course we don't. The computer does it for us and gives us the associated p-value. Okay, there is no answer to the question, which one should I use? Okay, I wish there was. I'm continually asked it by fourth year students, by master's students, by PhD students, by members of staff. Which is the most appropriate post-hoc test? Up to you. Okay, you do have to think about it. You can assume that there is no effect methods. Okay. That's the standard sets of them. We know that that's going to be conservative when the ANOVA indicates that there is an effect. Okay, so we're going to assume there's no effect, but that we know that there is one really, is necessarily going to be conservative. That means it's going to miss differences that exist. And you have to decide how important that is when compared to assuming there is an effect, things like the PLSD, where we're not doing the appropriate correction for the number of comparisons. We're assuming that effects that we detect without doing that correction are significant. That's going to be prone to type 1 errors. You have to do those balancing acts. Do you use the studentized range methods, or do you use the adjust alpha methods? Again, depends on the relative importance that you attach to saying differences exist when they don't, or missing differences that do exist. Type 1 versus type 2, you've got to decide on the balance yourself. And so long as you think about it just a little bit and say, we're going to use this sort of test, you don't have to justify it, but you have to say what sort of post-hoc tests you will use are. Most textbooks, rather than many, but most, advocate the studentized range. Tukey's method is typically seen as the preferred one. Okay, but remember, inclusions of levels on things which have a natural boundedness, so stimulus orientation from upright to inverted. If you add values in between, well, it makes it harder to detect the differences between upright and inverted. And it shouldn't do, because if there are effects there, they don't depend on the number of other comparisons. So you need to be cautious about just willy-nilly using studentized range or how you use them. Okay, so these can be suspect to type 2 errors, not detecting differences that exist. Again, that might or might not matter. You have to think about, in your study, how much do these things matter? Okay, and there was a period, I think, when psychology papers were coming out with lots and lots of differences, and people getting bogged down with differences that weren't real, and so they went very, very conservative. My suspicion is that there's now going to be a period where that conservatism is relaxed a little bit, and people will be going, you know what? If somebody says there's a difference, but there isn't really, we can cope with it. It'll be an interesting test of the maturity of the discipline, to see how well they deal with the relative risks of type 1 and type 2 errors. Okay, so unfortunately no ideal exists. What's your null hypothesis? What's, probably more importantly, what's your alternate hypothesis? How much does it matter? And my advice is just read what other people do in the area. It well might be that there's consensus on what to do that's based on nothing more than just history. But at least there's a consensus there. Okay, so it might not be the most appropriate, but it's the safest. Okay, and only deviate from those if you've got good reason to, or are willing to have the argument. I'm always willing to have an argument, particularly when somebody says, doctrine says it's this way. That just means that it's doctrine. It's the way that everyone does it because nobody's thought about it and they can't defend it. And those are always the arguments that one can win, so it's fun. But in general, see what people do and copy it. Okay. That was all dealing in a sense with comparing means, one-way ANOVAs, or looking at main effects. Same applies if 2 or 3 or whatever way ANOVA. Looking at main effects, you use one or other of those techniques. If we think of a two-way, we're manipulating or hoping to manipulate, change the dependent variable by targeting two aspects, two processes of what's going on. Okay, so we have a factor 1 effect, a factor 2 effect, and this interaction effect, this dependency, that the impact of factor 2 depends on the level of factor 1. Okay, and we have again our slightly longer model, and we have our summary table that will come out, which will give us the probabilities of the F value for factor 1 equaling 1, the probability of the F factor, the F ratio associated with factor 2 equaling 1, and the probability of the interaction term, the variance ratio of the interaction term equaling 1. Okay, so we've got two main effects and an interaction term. The main effects tells you simply, are all the levels of each factor the same? It's averaging across, looking across, so independent of the levels of factor 2. And then the main effect for factor 2 is, are the means of the different levels of factor 2 the same, averaged across or independent of the level of factor 1. And then the interaction term says, are the effects constant? Okay, what that's really telling us is looking at the differences between the levels of one factor, and are they the same regardless of the instances of the second factor. Okay, so when we look at this, if you've got a main effect of factor 1, so A, B or C in capitals, are these means statistically the same? The main effect of factor 2 is looking at the little a, little b, the red versus blue, and saying if we average across the different levels of factor 1, are they the same? Are the means the same? Okay, so the interaction term is saying, well, if we took, for example, factor 2, A versus B, we've got a difference there. Is that difference the same for each condition? Okay, so there the difference is bigger, but in the same direction. In that one, well, it's upside down. So overall, on average, factor 2 level B, little b, is bigger than little a. Here, little a condition is bigger than little b. And then we're back to a situation there where at least it's in the right direction. But these differences are very much bigger than those. So there's an interaction going on. The difference of the difference is not the same. So in this one, little a is, say, plus, does that look like about 15 bigger than here? Whereas here, little a is about 20 less. So you've got plus 15 versus minus 20. It's a difference of 35 of the differences. And that, the significant interaction is saying that sort of thing, that difference of the difference, is significant. So with a non-significant interaction, the differences are roughly constant. With a significant interaction, they change. They're not the same for each condition. Okay. With a two-way ANOVA, the interaction term, if it's significant, is the one that you need to look at first. Okay, so the interpretation of main effects is going to depend on the interaction. Okay, so if there's non-significant interaction, life is relatively straightforward. You've just got the main effects to deal with. You treat those exactly in the same way as you do for a one-way ANOVA. You've just got two sets of them to do, possibly if they're both significant. But you've just got main effects to deal with. if you've got a significant interaction, there are several possibilities that will lead to different interpretations of the main effects, including, incidentally, when there is no main effect. Okay, so top left, condition 2 is bigger than condition 1, and it doesn't matter whether it's level A or level B. So there what we've got is two main effects of the red versus blue, and this condition here of A and B. Okay, if we go along to here, what we have is that for condition A, the blue is bigger than the red, as it is for B. But the difference of the differences is significant. So that difference is bigger than that. That's an interaction term. But it's not going to change the interpretation of the main effect of AB or of blue versus red. The blue is still always higher than the red, and it increases going from A to B. This one, we have an interaction effect and no main effects. Okay, so if you average across A and B, the points are here. And indeed, if you average across the red and blue, the point is here. So all of them, on the main effects, the means are the same. But there's clearly a difference. It's just that here, the blue is higher than the red, and here the red is higher than the blue. So we can't and shouldn't conclude that there are no main effects. There is an impact of changing from A to B. It just doesn't show up in the main effect, but it does in the interaction term. And in this case, the red and the blue are always different from each other. So at no point are they the same. It just depends which level you're looking at as to which is higher. Here's another example of an interaction where the main effect is of the red versus blue is only evident under condition B. There's a difference here, but not in condition A. So there are main effects going on of red versus blue, but only in condition B. And so we can only make sense of our main effects once we consider the interaction terms. So in a two-way ANOVA, if you have a significant interaction, or three-way ANOVA, any n-way ANOVA, with a significant interaction, you need to look at that first. And the first thing to do is to plot out your data and just look at it. That will nearly always allow you to see where interactions are going on. To look at the difference and see, so this could come down again, but if this difference is the same, so if the lines are parallel, then there isn't an interaction. Okay, and if the ANOVA tells you that there is an interaction, you want to look to see where the lines diverge or converge. Look where the differences change. So that's likely to be an interaction. That's likely to be a source of the interaction. Okay, so the interactions are, in a sense, more important than main effects. And you mustn't interpret main effects first if you have a significant interaction. If the interaction is non-significant, it doesn't matter what the lines look like. It's saying, actually, we can treat these as having the same difference. It's just an illusion. It's a pattern that isn't really there in the data. Okay, so constant main effects, no interaction, the lines are always parallel. Here we've got two main effects, but the lines aren't parallel, so you'd expect to see the interaction. If you see the interaction, plot the data. This is a quick way of getting a feel for where the source of the interaction is going to be. Okay, so this difference, B, is much bigger than A when factor 2 equals 2. This one goes up. You can play these interactions either way, Go back to this one. There's a bit of a difference here and a bigger difference here. The other way of looking at it is, rather than looking at it like that, is to look at the changes that way. So B is only a little bit bigger here, whereas it goes up a lot more there. So there's always two ways of phrasing and thinking about interaction terms. And again, you need to think which way round you want to express it, which way round fits with your hypotheses. And it's easiest to relate to the hypotheses is the way that you should express the interaction of terms. No main effects. And then you've got two ways of doing it. So 2 is bigger than 1 when factor 1, or 1 is bigger than 2 when factor 1 equals B. You can change that around. Whichever way ties most neatly with your hypotheses is the way to think of it and discuss it. Here we have 2 main effects. So on average, the red is higher than the blue. And on average, B is higher than A. 2 main effects. Of course, there aren't. You've got a big interaction such that there's only a difference under condition B. So they really are important, and the thing to do is always graph your data to have a look at it and decide which of the 2 ways to describe the interaction is the most appropriate, which is the way that ties most neatly with your hypotheses. Okay, what do we do then with a 2-way ANOVA? So this is some data of the money that was spent going to a cinema. It's fictitious data. And we have different ages. So you look at children under 16, those 16 to 18, or 16 to 21, and adults, parents. And you also look, because I'm old-fashioned, you look at, do the men tend to spend more than women, particularly if they're going as a couple? Does the man still pay for the going to the cinema? Okay, so you run the ANOVA, and you find that there's an effective age group and an interaction of age group by gender. Okay, so as soon as we see the interaction, we go, aha, we've got a main effect and an interaction. We've got to look at the interaction first. Okay, so we're going to try and start to uncover that dependency, which is all that the interaction means, that dependency between things. So there's an effect which is moderated, the size of it depends on, moderated by the other factor. So the first thing, we just plot it out. We look at the means and the standard errors of the mean. Okay, so we've got adults, teenagers, children, by the 2 genders. And the quick eyeballing of that suggests to me that children, it doesn't matter about gender. With teens, it's probably males spend more than females, whereas for adults, they're roughly the same. Perhaps females spending a little bit more than males. Okay, so just by looking at that, the way that one describes this naturally implies an interaction. There's no difference there. There might be a small difference there, but it looks as though there's a difference there. That's a dependency. Spending is moderated by the age or the gender differences. The gender spending is moderated by age. Okay, so we've already sort of answered the question. We know what we're expecting to see. So we're going to start with what's called a simple effects analysis. Okay, so what we're going to do is say, well, there's a difference in gender spending. So we think that the red and blue lines, the differences differ. So we're just going to ask, is there an effect of gender on each level of age? Okay, so we're going to take one of these and we're going to calculate the standard deviation of the difference to calculate our t-values. It's always done by 2 times the mean square error term in the harmonic mean. The harmonic mean is the number of samples divided by the sum of the 1/overs, the reciprocals. So this is called a reciprocal of the n level. So the sum of the reciprocals, and there's the number of levels. We calculate it like that just to allow for different n's. Okay, but we're going to just use this to calculate the standard deviation of the difference. And then we can say for gender, our estimate of the standard deviation of the difference is this. This value, the mean square error, comes from that F table and is just the error term associated with gender. So it's 2 times that divided by 10 and has 54 degrees of freedom. So we calculate our t value as the difference for each group, as the male minus female, we could do female minus male, divided by that standard deviation. So for adults, we have a difference which is non-significant. For teenagers, there's a significant difference, and for children, there's no difference, non-significant difference. Okay, so what we can say is that there is a gender difference for teens, but not for children or adults. And that's described that interaction term. And so by looking at the simple effects, we just ask, is there a gender difference for these 3? Of course, we can do the same thing and ask, is there a difference of age for the different genders? Come out as giving us the same answer. Okay, but once you've plotted the data in a way that makes sense, is easiest to understand, interpret the simple effects, the consistencies of them, in the way that's there and easily compared visually on the graph. So here we've got the genders next to each other. So ask, is there an effect of gender for each level of age? It's also easier if there's just a 2 level in one condition. Okay, we've got to do really the same for the age groups. So we get the look at this, because this is a within subjects design, between rather, this thing will always come out as being the same. Okay, so, but we do the same trick. We're now looking for age group. We're asking about the differences that we have. So the t values for adding the teens depends on the male group. So for males, there's differences for the teens, and comparing the teens with the children. Okay, it's slightly more, it's saying that is higher than that one and that one. Yeah, so there's more to do doing it this way, but that's higher than that and that, whereas these ones are all essentially the same. Females, there's differences. This is adult child and teen child, are significantly different as well. Okay, so you end up having to do quite a lot of little tests to look at the same things different ways to get the full description. Okay, so for males, the teen is greater than the adult and child. For females, the child is less than the other 2 groups. And we've also got the gender effect. So there's for teens, males are higher than the female, but not for the other 2 groups. So now, having done all of that, we put it all together. Okay. So here's one way of doing it, and we'll hopefully let you see why we do the interaction terms first. So we could do the main effects. Overall, the amount of money spent at cinema did not vary between males and females. Spend did, however, vary with age. Tukey's HSD post-hoc analysis suggested that teenagers spend more than adults or children, blah, 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 blah. The effects of age and gender were not independent of each other, the interaction terms, and now I've got to describe the interactions. Okay, so by giving all of the stuff to do with the main effects first, with that interaction, you still have to describe the interaction. Okay, simple effects analysis, so you'd have to put this lot in sort of anyway. Whereas if you do the interaction terms first, so you say there was a significant interaction, simple effects analysis of the interaction, there you go, indicated that while teenage boys spend more than teenage girls, there were no significant differences in the spend, etc., etc. Okay? And that allows me to say, overall, these results suggest that for females, spending increased from childhood and remained stable, whereas for males, there's a transitory peak during teenage years. And I don't really have to mention the main effects. Because really, what were the main effects? Well, they weren't there. It wasn't that teenagers spent more. It was male teenagers spent more than female teenagers. That's not the same as saying teenagers spent more. And the same with the gender. You can't say what the main effect might look like because it's contingent. So you have to undo all of the stuff that you said. What you will find, unfortunately, is that quite often the simple effects analysis does not reveal the source of the interaction. So here's a case where the red is always bigger than the blue, and the heights of them vary between them. So B is always, for factor 1, this one is always bigger than these, and then A, then C, then D. Okay, so there are genuine main effects going on, but this difference changes in this condition. So it's still an interaction term, but if you do the simple effects analysis, which you should do, you would find that the red is always bigger than the blue, that B is always bigger than A, and then A bigger than C, C bigger than D. So you've got constant main effects, they're always there, but still got the interaction term. Okay, what we have to remember is that the interaction says the differences are not the same size. Okay, so what we need to do, if the simple effects analysis doesn't give us a simple explanation, we need to do the actual interaction analysis. We need to look at the differences between these things. We need to compare that arrow height with that arrow height. And remember, we have to keep the sign of it. We have to do the red minus blue, even if the swap around, keep the sign of the difference in there. Okay, so we've got to now start looking at the differences. Okay, and of course what we have here is an error term that comes not from the main effect, but directly from the interaction term. But other than that, we do the same thing. We look at those differences in the means, and we compare them as though they were, well, using either a t-test, or if we're using a studentized range, Q. Okay, so we've got the error term, but now it's the error terms in the interaction that we're using, the difference of 1 and the difference of 2. Okay, but we're still looking at those differences, but now we are looking at the true interaction, the difference of the difference. Okay, so we're just going to do exactly the same thing to work it out. So, interpreting the results from an n-way ANOVA. Okay, we're going to have potentially main effects and interactions. Gone over the reason why we must always analyse interactions first. Okay, we've got to make sure we know what we're talking about, otherwise you'll just do an awful lot of work to undo it all. And the way that you think about it won't get all of the details of these moderations, these dependencies, clear in your mind, and it will become much more jumbled. For the post-hoc analysis of the interactions, start by plotting your data. As soon as you get data, always just plot it first and then think about what to do. Okay, but then do simple effects analysis. That is often all that's needed. It will allow you to talk about, if you like, the source of the interaction. will allow you to describe the pattern of data in a succinct way. There was an effect of spend for difference in gender at the teenage years. That's an interaction. But you don't describe it in a sense as the interaction. It allows you, the simple effects analysis allows you to describe it in terms of your hypotheses, in terms of your data set. If that doesn't work, you have to analyse the difference of the differences. Conceptually, it's doing exactly the same thing. You just have to remember that interactions are differences. A significant interaction means the difference is not the same across all conditions. So start with the simple effects analysis. If that doesn't give nice clear results, then you have to repeat the task with the difference of the differences. Okay? Some of these are really quite tricky to do in SPSS. And you end up having to do them by hand. In the second part of the lecture, we'll get on to how you can actually speed that process up by making them planned comparisons. To summarise post-hoc tests, you should correct for multiple comparisons. Think carefully if the studentized range is the appropriate way to do. If it is not, so if you're dealing with a continuous variable and it should be bounded, it shouldn't just keep increasing and increasing, but it should be limited, then go, rather than the studentized range, think of changing alpha. Sidak's method is the method of choice. Unless it really doesn't matter if you say that there are differences when they're not. Okay, so balance of the type 1, type 2 errors. Interaction terms, interaction terms, interaction terms. Soon as you get them, deal with them. Start to work it out. Plot out the data. It's going to allow you to interpret complex patterns of results, this idea of dependency. And you must work out and look and analyse your interaction terms before looking at main effects. You don't know how to interpret main effects until you know what significant interaction terms mean. Quite often people have what look like differences consistently. The interaction term says actually they're not, and people just make a hash of interpreting their data. They don't take account, don't do the careful analysis of the interaction terms first, and start with simple effects analysis. In most of the experimental themes that we've got in the afternoon, that should be enough for the simple effects analysis. Okay, we'll have a 10-minute break and then we'll get on with hypothesis testing. So the idea of setting up very specific predictions and testing them using ANOVAs. Okay, let us continue with the hypothesis testing. You should and have been spending time developing your hypotheses. Okay, the more precise the hypothesis you have, the easier it is to evaluate, the easier it is to assess them if they're precise. So if you have value x will be half the value of y, you've got a really neat, clean thing to do. You get your estimates for each participant of x and y, you halve the value of y, and you ask, does x equal half the value of y? Okay. The value will increase the value of my, it should be dv at the end there. So if I'm predicting to increase my dependent variable by my manipulation, it's easy to test. You just ask, is the difference bigger than 0? Okay. You can only test your hypotheses directly in this way if you have a precise hypothesis. Okay, so the idea of these a priori tests, you've decided them beforehand a priori, is based on the theoretical considerations. They can be known as contrasts or planned comparisons. And ideally what you want are what are called orthogonal or independent contrasts. the planned comparisons. They're things where the result of one has no impact on the result of another. You're not using the same data twice. Okay, so we're going to look at some of these and how to do them. Okay, so if we did a one-way ANOVA, so we're going to estimate 3 population means, mu1, mu2, mu3. Okay, the ANOVA examines all linear combinations of those, all at the same time. So it asks, is the difference between mean 1 and 2 0, mean 1 and 3, mean 2 and 3 0? Those are the simple pairwise comparisons. But it also asks, is mean 1 minus the average of mean 2 and 3 0, and so on. You can imagine all hell starts to break loose when you have 4 levels in your ANOVA. Okay? What the Sheffey test does is all of these. So rather than just the 3 pairwise, it includes all linear combinations as the correction term. It's very conservative. Contrasts are about examining combinations of these. Okay? So you want to compare some mean, a combination of means, with another combination of means. Okay, so we can ask, is mean 1 the same as the average of means 2 and 3? Doesn't mean that they're the same as what 2 and 3. It's asking if it's the same as the mean of them. So we can take the combination of interest, and if it is the difference between 2 means, 0, we do a t-test. We can calculate the midpoint of the mean of the bars have slipped. So the mean midpoint as the mean of points 2 and 3, and calculate the difference of an observed value, condition 1, between the midpoint, and use a t-test to confirm, to examine the significance of the comparison. So if we can set it up so that we've got a thing where the difference is 0 that we're expecting, we do a t-test. So if you're expecting the values from a study to lie at the midpoint between 2 others, and that's your hypothesis, so theoretically that's what should happen, you can evaluate it directly. You take the midpoint, the average of means 2 and 3, and ask, is the difference of mean 1 minus mean 2, is that on average 0? A t-test against a hypothesized mean of 0. Okay, so if you've got a nice specific hypothesis, you can do these things as a t-test. And it means, in fact, that you run the omnibus ANOVA and report it, including the significant interactions and main effects, but then ignore that, essentially, because your hypothesis that you're testing is a beast like this. When we're doing these, we always want to know effect sizes. We do it in the same way as always. We use the sums of squares to calculate. We have an eta squared, which is the proportion of the contrast, sums of squares over the total. Partial eta squared is the sums of squares of that contrast, divided by the contrast plus the error term, so the proportion of variability that you could expect it to be able to explain. And we can use the r squared as the proportion of the main effect that the contrast explains. How much of the main effect or interaction does the contrast explain? They're all legitimate ones to use, but you should always report and make clear which one you are reporting. So partial eta squared, the r squared, or eta squared, when you're reporting the effects of a contrast. You don't just want to say that the contrast was significant, you want to say how significant it was. It's a size, if you like, rather than its p-value. SPSS churns out automatically for you contrasts. It does the linear contrast and polynomial contrasts. Okay, so you should put things in order, particularly if it's on a continuous scale. Make sure that what you're labelling category 1, 2, 3 and 4 are monotonically increasing if you can. So if it's different angles of orientation, make it start with upright and finish with inverted, and these intermediate ones be in the right order. If it's dosage, have the low dose at the left, the higher dose to the right, intermediate ones in order. Why? Because SPSS will automatically ask about and tell you about the linear trend. It will do the linear contrast between them, and it allows you to say whether there is, so if it does the linear contrast in the output is significant, then you can say that the values increased as dosage increased, or if the graph goes the other way, the values decreased as the dosage increased. Okay, so it does 2, and then if you've got more than 3 values, it will do in this case a quadratic. It actually fits a quadratic shape, a U shape or an N shaped curve to the data and says, is there a trend that goes like that? So if theoretically you would expect to see, say, recency and primacy effects in a memory task, so memory for things that you first learn, so the primacy ones, the first things you learn, you remember better, and you also remember the things that you've just been told better, but not the ones in between. You expect a curve of that shape, then look at the quadratic. It will tell you if there's a trend for a U-shaped response curve. Quite often, it doesn't make sense to do these sort of things, that these are genuinely categories without ordering, that there's no theoretical explanation. Unfortunately, there is no way of turning off SPSS, churning it out, so you can ignore that chunk of output. But that's what it's doing for you automatically, is putting in these sets of curves for it. And these sets happen to be what are called orthogonal. They're not dependent on each other. Okay. Running lots and lots of different contrasts is really not straightforward. Okay, they need to have this orthogonality component. Because what the contrasts are doing is splitting the sums of squares of that effect, whether it be the interaction or main effect. It's taking that effect and separating them out. Okay, and in fact that's one of the ways in which, in the nitty-gritty of the way SPSS does the calculations, it actually does all of the possible contrasts. Does the full set of orthogonal contrasts, adds them all up, because that's much quicker and easier than doing the full-blown thing. Okay, but each contrast you do uses, if you like, some of the sums of squares. It takes them and it's used them. Okay. And if you try and run too many contrasts, you're going to run out of your sums of squares. So you will end up with meaningless results. More importantly than that, if you're running 2 contrasts, they need to be independent of each other. You can't use the same sums of squares bit more than once, because then you're doing multiple comparisons with unknown quantities. So you have to try and make sure that each test is using a different set, different part of the sums of squares. Okay, you don't want to be artificially creating them. Okay, because that's what using something twice is doing. Okay, it's always possible to do it, but it can get complicated. What we want to do is have these orthogonal or independent contrasts. These are a pain in the backside to do in SPSS, and I'm not expecting you to do it. If you're doing a design where your supervisor ever says you have to do planned comparisons or orthogonal contrasts, you use R and get your supervisor to tell you how to do it. Otherwise they have been to my lecture but don't actually know themselves what they're talking about. Okay, we've got a whole lot of things, and we're going to ask, in one instance, do drugs 1 to 4 have an effect compared to control groups? So we're going to set up a contrast which is a quarter of that plus a quarter of that plus a quarter of that plus a quarter of that, which equals 1. Is that the same as that averaged and that, which is a half of each of them? Contrast we're going to compare against a value of 0. So what we do is we have the weights are quarter, 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 minus a half, minus a half. So we multiply each of these values by the weights, and we're going to ask if it equals 0. Yep, so that's our first question, is just, does the average of these equal the average of that? We can now ask about the relationship here of is 1 less than 2, less than 3, less than 4. So we're going to do it as a linear thing. We're going to ask the linear interpretation of just these 4 means. So, and to do that, we have weights of minus 3, minus 1, 1, 3, 0, and 0. Okay, these numbers, actually, if you multiply these 2 vectors together, come out as 0. It all cancels out, which is what orthogonal means. The dot product is 0, if you know your maths. Okay, these things, these weights, is the whole art of setting up these contrasts. Okay, and you have to get down to the L or the M matrix in SPSS to do it. It's a pain in the backside. But conceptually, you can see that this is just increasing, and it comes from minus 3 plus 2 plus 2 plus 2. And we're ignoring 5 and 6. We're just asking about these ones. The sum of these weights is 0. So we're doing a contrast. We're just asking, when we multiply 3 plus minus 1 plus that, is there a linear effect of dose? We can ask, are these two the same? So one is plus 1, the other is minus 1. Is the placebo effect the same as no drug? Or is there a placebo effect? Okay, now in this example you can actually do these sorts of things. You just take these values and multiply them. Okay, and then you're always asking, are they 0? So if the weights sum to 0, when you multiply all of those, they should all come to 0, if the means are the same. Okay, so you can imagine that this gets, this is a relatively simple example. But really what you're always trying to do is get a combination of these values of your means, of your estimates, and just saying, can we get them so that they meaningfully add up to 0? So is the average, is there an effect of drug versus no drug? Is there an increase? Do we have this pattern in our data? How likely is it that that pattern exists? We set up this planned contrast. Now, you have to do this thing of once you've got these, you've got to take these, or one way of doing it is take all the positive value ones, and then you can split these any which way, and you know it's going to be orthogonal to the rest. What we normally do is actually try and target and do just one contrast. We take our hypothesis and we build up the thing of, if for the null hypothesis is the data points will lie here, or they'll be bigger than, we set that up and do the one specific contrast. But you can, as you can see, do more than one in an appropriate way, but it needs quite a lot more thought. Okay, it does have in SPSS a number of built-in contrasts, some of which are orthogonal and some of which are not. If you ask about deviation, then it's just telling you whether each level mean differs from the grand mean. Okay. The simple one, so on the drop-down menu, one of them is called simple, and it's deviation from a control group mean. For that to work, you have to put the control group as either the first that you enter in or the last. And so the order in which you put things into your ANOVA in SPSS matters. There's repeated, where it compares the mean of group 1 with group 2 with group 3 with group 4, and so on, all the way along for you. These ones are not orthogonal. That is, here you've got a dependency everything on the grand mean. So you're using that value more than once. The simple deviation is always compared to the control level. Okay, so that they're not truly orthogonal. You can still do them and still interpret the outputs from them, but you just need to be a little more cautious. The polynomial one is the one that it does actually also by default. When you run SPSS, you'll often see contrasts, and it does these ones for you automatically. I've talked a little bit about them. The difference one compares the mean in each level with the average of all the previous levels. So it compares group 2 with group 1. It then compares group 3 with the average of 1 and 2. It compares group 4 with the average of 1, 2 and 3. Why you would ever want to do that, I don't know, but hey. And the helmet one is essentially the reverse of the difference one. So it compares group 1 with the average of all of the others, group 2 with the average of group 3, 4, 5, 6, group average, and then group 3 compares with the average of 4, 5, 6, and so on. Okay, again, they're built in there. This is just so that you know what they're doing. The most common one to use actually is this one, the simple one, where it's the deviation from the control condition. So either the first or the last group, you can specify which one. In general, you'll find that you actually want to just do this very specific one that you've set up. The theory says X will, a measure will equal something else, some other combination. And that's the only one that you set up and have to do. So we can use contrast to test our hypotheses. They actually give more power than doing the post-hoc tests. Okay? So you have to use them properly, but if you use just one or two, then you actually have more power. You've got more ability to detect differences that exist by doing contrasts than you have by using the standard post-hoc tests. Okay. You just have to make sure that all of the weights sum to 0, that you've got some combination of means where one set of means equals another set. When you do that, you can then make it sure that it equals 0 and then use a t-test. If at all possible, keep your contrasts, if you have to use more than one, keep them orthogonal. Make sure that they don't deal with each other. The easiest one is that example where it splits. If you take one set of your weights, you'll have some positive ones and negative ones. It's the only way for them to add to 0. You can do whatever you like with all of the positive weights that are left, or all of the negative weights. You can do what you like within those groups again. That will guarantee orthogonality. Okay, so formally it's if the dot product, the sum of the product of their weights is 0, then they will be orthogonal to each other. Use the built-in ones if you can. Okay, you have to use the L matrix or the C matrix or the M matrix depending on the things. You have to get into syntax if you really need to use them. As I say, there's quick and dirty ways is to just do the one contrast, the one comparison as a t-test. Calculate all of the values. Look at those differences. So multiply out the weights. So showed you the example of does the x1 is the midpoint of the other two. Calculate those and then you've just got a whole long list of numbers for each participant, and then you can take all of those numbers and say do they equal 0 using a standard t-test. So you can do the calculations for these things rather than use this beast. You can do the calculations essentially by hand and get the final t-test done. Okay, to finish up with, you will, I hope, on occasions get significant effects in your ANOVAs. If there are only 2 levels in a factor, or factors, you don't need to do extra analyses, because if there is one group is significantly bigger than the other, that is the own or different from, you know which non is numerically bigger than the other, and it must have that significance level. When there are more than 2 levels, it starts to get a little more complicated. If you have no a priori idea of what might happen, so if your hypotheses are just these might be different from each other, you have to use post-hoc tests. So when you run your ANOVA, get it to put out, always you click on the options button in SPSS. In there you always want it to give you the means, so you select all the groups that you can, drag them over to where it's going to give the means. Underneath, say compare main effects, check that box, use the drop down and click on Sidak's test. Okay, unless you're going to be use the PLSD, if there's good reason not to use the Sidak's, then use PLSD test. Okay, then get it to tell you it's the one that in that same box where you say, I want it to tell me the effect size. Okay, it'll give you then the partial eta squares associated with all of the ANOVA components. It's the one where you say, do the homogeneity tests, which it'll do if it can, and so on. In that box, get it to do these post-hoc tests. You can also get it to do Tukey's HSD for between subject factors. There is an option there for post-hoc tests. Whenever you see the button for post-hoc tests, so post-hoc ... click on it. See if there are post-hoc tests that you can do. If they are, I would suggest starting off with just using Tukey's HSD, unless you have this idea of a continuous variable, in which case just stick with the alpha correction values using the post-hoc tests, so Sidak's correction, comparing the means. If you have got a good, clear hypothesis, and you should have, then use the contrasts. There will normally be just one contrast, but you need to think about what it's going to be. How are you going to take your data and calculate these weights, if you like, calculate it so that you're looking for a difference against 0. So if you think of, often you say this one, no, one number should be bigger than another, that's easy. You do the subtraction, because the null hypothesis is that they're not bigger than each other. If you do the subtraction and compare it against 0, it'll come out as being significant or negative. Numerically it's negative, you can reject the one-tailed test automatically. But often you can get more sophisticated ones. It's the value halfway between 2 data points. So is x1 different from the midpoint of x2 and 3? Calculate the midpoint, the average between 2 and 3, and subtract it from x1. If x1 is on average at that midpoint, then that difference should be 0. So you do the t-test of all of those subtractions, and for each participant, in each condition, you do calculate the midpoint, take the difference of the observed value from the midpoint, gives you a long, long list of numbers for each participant. You then ask, is that number, on average, can we distinguish it from 0? If you can, x does not lie at the midpoint. Okay, so try and use them. Keep the number that you do to the minimum. Basically the thing. Normally by the minimum I mean 1. You might occasionally want to do 2. Okay. So that's it. Thank you for the small number of you that turned up. I'll be around at 2 o'clock, because you should be now starting to move into trying to implement your designs, implement your studies. Do come along at the allotted time, particularly if you want to, well, except for the 1 o'clock one, if you want to talk to either myself or Justin in your groups about your design. But you should start to be thinking about how to implement it. So that's getting your stimuli together and running it within cog demos or whatever system you want. We have E' there. There's other ways that you can do it. We don't mind how you get the data input, but it needs to be some way of taking a accurate measure of your dependent variable and then being able to get those data out.